Welcome. I'm Bill Wake. This is my weekly summary of Twitch. Lately, we've been working on a programming language called Tenth, developing the interpreter and the compiler, and then finally a little hangman game to demonstrate that they both work. So this is the wrap up. We've finished our last broadcast on that, so I thought I'd go over kind of the whole thing at a high level anyway. All right, so we'll take a quick intro to Tenth, the language. We'll talk about dictionaries, primary and secondary words, meta and regular words. We'll show how to implement repeat until, and we'll talk about strings and then do a quick demo and a little bit of the code for Hangman itself. Tenth is an imitator of fourth, or it's kind of a subset, maybe an extended subset. And basically it's a stack-based language. So the core of it is there's a stack. You can manipulate values and put them back on the stack. And then there are control structures that can work with them in a procedure calling mechanism. It's a fairly low level language, not assembly language, but not super powerful. There's no concepts of objects or exceptions or any of that stuff. All right, so if I want to do 1 plus 2 times 3, all right, I push the values on the stack. Now, if I do plus, then I'm doing the plus first, but I want to do the multiply first. So I push the 3 and then times and plus. And at that point, I'll have 3 values on the stack, times multiplies 2 times 3, plus adds to that, and there'll be a value left on the stack. You don't see it by default, but dot is a print that shows us the top of the stack. So 2 times 3, 1 plus 2 times 3 is 7. Okay. You can also define words. So let's define add double. We'll say we're going to take 2 values on top of the stack and add them, and then take that times 2, and that'll be what we do to it. It'll leave 1 value on the stack. So the colon says this is a definition, and it runs now. Okay, we're defining a new word. Add double is the word, so it keeps that aside. Now plus, normally it would add something on the stack, but we're in compile mode with entering colon, so it just saves that word and saves the word for 2, and it saves the word for times, and then semicolon says our definition is done. Okay, so at this point I can do add double again. So if I add double on 10 and 7, add double, all right, it'll take 10 plus 7, 17, times 2, 34, and then I'll print, and I expect to see 34. That's kind of the essence of what's going on. The other piece I'll mention briefly is we do have control structures. So we have if and repeat until and while. Is it 0? Okay, and so we got colon and that defines something. Is it 0? Well, we'll assume the value is coming in on the stack. We'll take 0 equals, so that turns it into the Boolean true if it's 0, and we'll do if, and if it's true, we're going to say yes, and then otherwise we're going to say no, and phi is the end if. All right, so this thing takes a value on the stack. The if will consume it. Well, the 0 equals will consume it, and then the if will consume that, and it leaves a string on top of the stack. Okay, so we still have 34 on top of the stack. So is it 0? And then we'll print the result, and dollar print strings. Okay, and we expect no. Okay, but if we were to push a 0 on the stack and print that result, we expect yes. Okay, so that's about the briefest tour I can give you, showing off the stack nature, showing off definition, and showing off one of the control structures. Okay, one of the concepts is that the words you define and the system words that are already defined, they're maintained in a dictionary. A dictionary for us, it's just a singly linked list, and it's got information. It points to the previous entry, and it also knows the string it had, and it also points to the code so it can, once it finds it, it can execute it. Now, this is, you can tell this is kind of a slow interpreter approach, right? Um, it's going to walk through all the list of words to find them. But most of this comes at compile time. So there's, you're not running through the dictionary at runtime. It's only during compilation. So the cost is not so bad. We might have, I don't know, you might have a couple hundred words. It's zipping through a loop. It's not that slow even at compiler time. All right, but what we'll see is there's this structure for dictionary entries, and it forms a singly linked list. The user-defined words just end up at the front of the dictionary, and the predefined words in the back. Forth, the programming language, has a mechanism where you can kind of build tree-shaped dictionaries. Start a vocabulary and then make another vocabulary depend on that, but another place might depend on the original vocabulary. We're not doing anything that fancy. All right. So for us, there's two kinds of words. One is a primary, and a primary is just an assembly language routine. So there's no, there's no interpretation once you get to it. All right. So the dictionary entry on the left there, it's got the link to the previous. It pointed to the name, and then it just points to the address of the code, something that's the address of the code. So it's an indirect pointer. And then the primaries, they just have a big table with those three entries, just for a whole block of those for the primaries. Now, secondaries, those are user-defined words, and they look similar. The header's the same. There's a link to the previous entry, a pointer to the name, and then we have the address of the code that we're going to run. It's going to be an assembly language routine, so in a sense, it's a primary, but start2d for start secondary is it interprets things by saying, I'm going to get the next word after me, and that's going to have a list of addresses, just each word that's in that definition. So we defined add double, and it was plus 2 times or whatever. Those words are going to be in there in a list. And then always we generate N2D, N secondary, as the last thing in the list. So the start2d knows how to interpret. It walks through that list. It eventually hits N2D, which says, okay, we're done. Let's look at more detail on the header. So we have the link to the previous. So that's for the dictionary. We have a pointer to the name of the routine, which is a string off somewhere. And that's what we match on as we're walking through the dictionary. And then we have the address of the code. And notice that both primaries and secondaries have that address. So we can treat them the same. There's no distinction at runtime between calling a primary and calling a secondary. The whole setup is indirect threaded code. Indirect, since this last cell points to the address of the code, not the code itself. That's the indirection. And then it's threaded, since secondaries can point to other secondaries, and it forms this big kind of tree structure implicitly. All right, so let's look at a primary. On the left, we have the definitions we're going to use. So they're very low level for us. We have a stack pointer. We call it VSP. That's a register we dedicated to being the runtime stack. And so pushing something is store it at the stack and increment the stack by 8. And then pop is the opposite. Load something from the stack and, decrement by 8. Okay, and so using that, we can define data pop AB, which pops 2 things. And so it just calls data pop for the first one, data pop for the second one. There's a convention that A, B, and C are just kind of the usual names for the first, second, and third entries on the stack. Okay, now given those, we want to define the add routine. Now the heart of it is clearly that instruction line 29, the instruction, add x0 gets x0 plus x1 is how you read that. The rest is the overhead of kind of working with the stack. We first have to pop x1 and x0, then add them, and then we push the result and return. So you can see as an interpreter, it's got a little overhead compared to a compiler. A compiler would keep track of what variables were in what register or memory, and then it would focus on that add instruction. And we have to have a few more instructions. All right, now let's take the sample secondary. So, and I called it double sum here, but it adds 2 numbers, multiplies the result by 2. Okay, so the definition is going to create a dictionary entry, and so in memory, um, we're going to see the header. Well, first we've got the double sum string. Uh, it's going to get zero terminated, and then there's some filler bytes to make sure everything lines up to a 64-bit boundary. And then where it says link to previous, that's going to be the first cell of the header. So it's pointing to the previous dictionary entry. The pointer to the name points back to double sum. Okay, so that's our definition. The third cell is a pointer to the routine that's going to get called. So it points to a pointer that points to the code for start2D. So that's that indirection. All right, but anyway, in any case, that's the routine that will be called to handle this block. Now, the code, the secondary, is just this list of other pointers, and we could put it right in, in this block of memory. It's fine. Another header will skip, another dictionary entry will skip around this code. It just lets us keep everything in one place. But so we point to that start2D pointer. Then the next thing is a plus. So it points to the plus routine. And then the third thing is a push for the 2. We don't just enter the 2 by itself. We store it as push followed by a word containing the constant. So we see the push and then 2 following it, and then a star, and then finally an N2D, pointer to N2D. All those are set up so that the start2D routine can just read those pointers, dereference them, and jump to the code that's being run. All right, so let's look at start2D and N2D. Back in assembly code, this is the kind of core interpreter loop. So we'll call standard Prolog first. That's just something we have to do when we call other procedures. But we have this virtual program counter, which represents where are we in walking through our program. It's originally pointing to that start2D instruction. We skip past it in line 48, and we get into the main loop. So 51, we're going to load whatever the virtual program counter is pointing to, which is the next word in the dictionary list, in the secondary list rather. We load what it points to. Okay, that's that indirect load in 52, and then 53 is BLR, is branched through with a link register. So we're saying branched with wherever X1 points to. It's kind of a dynamic branch, or dynamic procedure call, I guess you'd say. And then when it gets back from the procedure call, which could be the add or a plus or times or another secondary, this can be recursive, it jumps back to the top of the interpreter loop. And so it jumps back to line 50, and then repeats the process. So it's just going through. Now you might say, like, wait a minute, I've got a loop with no exit, but that's why we put N2D at the end of every secondary list. And so N2D says, okay, get the virtual program counter, restore it from the stack. So that's how come we can call it recursively, because we've kept the program counter on the stack in case it calls other things. And then we do our standard epilogue, which restores other registers and a return. So that's our exit, is that we eventually in our list we'll call N2D. All right, another concept we have is meta words and regular words. So we saw it briefly. Colon starts a definition, semicolon ends it, and then if, else, repeat, while, all those control words are also meta words. Their characteristic is they execute immediately, even in compile mode, versus regular words, which in compile mode we add them to that secondary list, but in eval mode we execute them immediately. So meta words are always in eval mode, if I can say it that way, evaluation mode. And things like plus, times, divide, those are system defined words. Most of them are regular words. Game loop, hangman, those are words I wrote, and they're user defined words, but they're also regular words. So the meta words are really definitional, and control structures are the big uses of that. Rather than look at the definition, how that works, I thought I'd take one of the easier control structures. So when we have constants, like we had 2, it turned it into push followed by 2. Now, we also define another couple of routines that are similar to that, jump and jump if false. So jump is followed by a pointer to where it should jump to in the secondary list. And then jump if false is also followed by a pointer. The difference is jump if false only jumps if the value it's looking at is false. Okay, so the code for it, jump is easier. It just says load the virtual program counter with whatever it points to. So by then it's pointing to the word after the jump statement that's the address we want to be our next word. So the LDR loads that register and with the indirect value and effectively moves the virtual program counter. Jump if false is more work, of course. So jump if false, we're going to look at the top of the stack, data pop x0. We're going to compare it to 0. And then if it is 0, we're going to jump down to skip if in line 66. Now notice that code is the same as our jump statement. It loads the virtual program counter. So we said jump if false, and here we are jumping. So that's how that one's implemented. And then it falls through the return. The other case, in line 63, we didn't take the branch and we just skip over the word that points to the address. So we're just moving our program counter past the jump if false, past the address it points to, and we continue again with the rest of the code. Okay, so these are kind of the building blocks for if, while, repeat until, and so on. All right, so let's look at how repeat until works. And then we'll go to the code. I'll show you the code for it after that. So a repeat until, you have the ... is some block of code, and you're going to execute that, and then you're going to leave a value on the stack, A, and the until is going to say pop that value, compare it to false. If it's false, jump back to the top of the loop. So I've shown it as start on the left there. If it's not false, in other words, the condition is true, well, we repeat it until the condition, we fall through to the code after the loop. Okay, and so we already looked at jump if false. It jumps if it's 0. All right, and on the right, I'm showing the secondary we're going to generate. So the code for repeat running at compile time is going to populate the secondary with the right code. All right, so the repeat, so the thing it does is it's going to push code address onto a control stack. So I've shown that on the left. We had some stuff in there already because we may be in the middle of nested control structures. So the repeat until uses this stack. Repeat's going to fill up the stack, until is going to clear it back down, and we'll be left with the else, the entries we already had. Okay, so storing the code address to the control stack. Well, that code address is the top of the secondary, or the next line in the secondary, and it's where we want to jump back to. So we're basically saving that return address or the jump address that we're going to put it to. Okay, so somewhere jump if false is going to jump back to that thing. We have to keep track of that until we're ready to do it. All right, then we have the code in the middle, code inside the loop, more code inside the loop. I'm assuming we're at address 20 for the code inside the loop, and then more code inside the loop. We're just generating those sequential slots by whatever mechanism, repeat until is not involved in this. It's whatever else is being compiled. Okay, then we get to the until, and until says, I'm going to generate a jump if false instruction, and where am I going to jump to? Well, I'm going to pop that off the control stack. It was address 20. And so I'll create the jump if false instruction followed by the 20 to represent address 20. And in effect, I've patched that code so it jumps to the right place. Okay. And so after that, there's code after the loop. We generate that in the secondary, and we're just going on with compiling at that point. Now, notice the control stack on the left, it still has jump for else and address of repeat. Whatever control statements are also being compiled. We don't, we're not affecting those. So here's the code for repeat until. Repeat, remember, it just pushed the next secondary address on the control stack. So we have a control push instruction. It's very much like our data push. It just uses a different stack. And secondary space is the register that is pointing to the currently built up definition. So we push that address on the stack, and that's all repeat did. When we hit until, then it loads the address for the jump if false word and stores that on the stack. So that it's the indirect word. We have to have the pointer to the jump if false, basically. And then finally, we pop that control stack into X0 and store that address into the secondary and return. So it's enough to put the jump if false and the instruction pointing back up to the top of the loop. And then whatever code comes after that is generated by other instructions. Given that, I thought I'd show how we compile strings. They're a little different. We put them in line with the code. We could put it in a separate area. It would probably be a touch more efficient to do so, but I'd have to manage another area. So I decided I would just keep them in line, sort of like we do with the numeric constants. Okay. What we're trying to generate is the push, and it needs to point to the string. Okay. And then we're going to, since this is going to be in line with our code, we're going to jump around that string. And so that'll be followed by the bytes of the string and then some padding bytes, because again, we have to keep 64-bit boundaries. And once you get to a round string, that label at the bottom, that's no longer our concern. Whatever comes next, generated code is what gets put in there. Okay, but there is this little push and a jump, and you'll see that in the code that generates this. So compile string, it calls a standard prolog, and then it's got to store the push. So it loads the push word address and stores it in the secondary. Then we want to get to the address of the string. Well, we decided it would be down where it says bytes of string. We know that's 24 words down. We started at the pointer to the string, 8, 16, 24, gets us down around that set of words. Okay, so we'll store the 24. We're going to push something. The string is going to be found 24 bytes from where you are. And then we push the jump. So load address for the jump word address, that pointer to the jump, and store that in the secondary. And then we are going to save that address because we don't know how long the string is going to be. We haven't dealt with that yet. So we'll push that onto our control stack, and I just push a -1 for now. We don't know what the value will be. So that's the word we're going to patch with the jump address. Then we call something to store the string. Well, we already have a method define string. It says write a string in the secondary space, finish it with a \0, make a null terminated, and then pad that thing out until it's 64 bits. Okay, and then finally we want to fix that jump, and so the control stack has the address of the jump instruction, or the constant where the jump instruction is going to use, and so we store the current secondary space into that location, and so that effectively patches that jump to point to the next address available for secondary space. All right, so that's all the assembly language we're going to look at for now. If you haven't seen assembler, I'm sure it was just kind of a whirlwind, but we have the compiler and interpreter for all our words. All that stuff is done, and let me just do a quick demo of the fourth system running our Hangman game we built. All right, just to make it interesting, I've already started the system up with the Hangman code in, and I put in a word, and we're going to pretend we're playing to guess it. Okay, so we start with just a scaffold. We've got the blank lines up top, the one per letter. Then we have the scaffold and our list of wrong addresses. So we'll take the old Ada Orange strategy. Okay, so does it have an E? Yes, it's got 3 E's. Okay, how about a T? A, O, I, N, S. Okay. And let's see, Ada Orange through SHR. Okay, well, I'm kind of ready to guess, so if there's an M and a W. Okay, so game over, you win. We got the somewhere before we filled out the body of the hangman person. Okay. All right, so let's take a look at one of the tests. This is the more sophisticated setup because we need some actual stubs, well, test doubles. Okay, so I'm going to define, in 207, I'm going to define an array that represents what's the next character read. So we're going to test the top level game loop, and it needs to read guesses and score them basically, and then stop when we get the word done or we run out of run out of hangman. So we'll store those expected those inputs in this read stub array, and we'll have read stub index that counts which entry we're on. Okay, so read stub init will take the string it's given and do a string to array, which stores it for each byte or for each character in the string. It stores it into a numeric word and then stores a 0 for the last one. And then we set read stub index to 0, saying we're going to start at this front of the array. All right, and so the test code is going to call read stub, and read stub is just going to fetch the next thing, the next character, and then move everything on. So next time after that, it fetches the next one. So it loads the stub array. That's the address of the array. It loads the index, and at gets the value. So if we're on in item 1, that'll push the 1 on the stack, and then at plus says read the array at whatever the index is. It's whatever number that is. And so that puts the contents of the array on the stack, which is what we need for a read routine. And then we increment the read stub index, and the next character, so it reads the next character. Okay, and then finally we have a stub for display stub. We're not going to worry about it. It's just going to be an empty routine, but we have to call the display as part of our game loop. All right, so let's test the game loop. I start off with the name, test game loop, and $. That prints the test game loops. Then I push 90210. Well, that's kind of an arbitrary number. I want to make sure my stack is being treated the way I expect. So I'm going to push it before I call my routine. And then you can see in 233, I check and make sure the top of the stack is again 90210. It was easy to make mistakes and get off by 1, read too much of the stack or read not enough. And so I started doing that kind of test around my normal tests. All right, and then the test itself, the kind of arrange section, we give it a word. Is a kind of lava, I guess. It's a common crossword puzzle word and a 2-letter Scrabble word. But that'll be our target, and we'll call game init. That's just sort of normal how you initialize a game. And then B and A are going to be our guesses. So we'll call those to read stub init. It'll create the array with B and then A and then a 0. And then we call the act code that is the game loop itself. Well, we have to give it a display routine, the name of a display routine, and the name of a read stub, read routine. And so those 2 arguments go to game loop. It's going to do whatever its job is, okay? And then when it gets back, we expect the clue, which is the total guess we've made. That thing we turn into a string. It should be however you say that. And we're going to make sure that's equal to it. So we should have guessed the word. The A should have caught all the A's. And then our wrong guesses, we'll make that into a string, and that should be B, okay? Because that's the only letter we guessed that was wrong. And we check that that's the right value. So clue, we had that at the top of the hangman that starts out all dashes. That's what gets displayed for clue. And then wrong guesses shows whatever the list of letters that were guessed wrong. All right. And then the game loop itself, it's a bit big-ish. I mean, I wouldn't want to go any bigger than this, but it catches the core idea of our game. So what we're going to do is, while the game is not over, I usually keep track of what is on the stack. So the read and display routines are there. Game over puts a Boolean on, not negates it, leaves it a Boolean, and then do reads it. And so it leaves the last 2 on the stack. So I'm going to duplicate the read routine. And the reason I do this is because I'm in a loop. I need to make sure when I get back to the top of the loop, read and display are on the stack. So I can't destroy them in this process. So I'll duplicate it. And that was the string read stub, or whatever we called it. And we do a call in 398. So we're calling our read routine, and we get a character back. We'll duplicate it so we have access to it for a little longer. We call update clue, which decides if it matched or not and gives us a status, Boolean status. And then if the status was wrong, then we update the wrong guesses. So that was the keeping track of that list of wrong guesses. Otherwise, we pop and get rid of the character. We don't need it anymore. We've already decided what it should do. Then we've got we exit the loop, or sorry, exit the if statement. We want the display routine, but we don't want to destroy it. So we do BAB, which takes the second argument on the stack and moves it to the front. So remember, ABC get used as the names of the top three elements. So BAB copies the second one down to the top. And then we call, and display gets called. And notice we have read and display on top of the stack, nothing else. So when it goes back to the do, the rest of it behaves right. Then at the bottom in 412, once we've said the game is over, we still have read and display. Well, now we can get rid of those. So we pop them twice. All right. And then all those other pieces, game over, update clue, update wrong guess, those are tested elsewhere. So this was just kind of a final high level test of the game loop itself. All right, and I'm not going to show the rest of the Hangman application. It's next time. I'm switching to a new project I'm calling Fume. It's a tool to explore money as streams and pools. So kind of keeping track of money for long periods of time and how we do that. So I'm starting that Thursday, May 9th, 2 to 4:30 p.m. Eastern Time, 6 to 8:30 p.m. UTC. And if you go to xp123.com/Twitch, that takes you to the live session. All right. Well, thanks for joining. This was a fun project for me. I'd wanted to do some assembly language programming. I hadn't done any in several years at this point, and I wanted to try this indirect threaded code technique. And it had been on my bucket list as a former compiler person. So I was glad to be able to do both those in this project and had a lot of fun. Thanks for watching. Take care. Bye-bye.